Right, what's up, Lehigh Universe? So thankful for all of you joining us in these videos. I just love to do this for fun. Uh, when I first started my physics career, undergrad career, um, I started with this course called Oscillations and Waves, and I actually really loved it. It was at the University of Toronto, and since then this course has been canceled. It's been, or not canceled, but it's been merged into a different course called mechanics. Um, and so, the experience that I got from oscillations and waves really helped me out throughout the rest of my undergrad, and the things that I learned really helped me achieve greater things in my upper year math courses and physics courses. So I just thought I would share some of this stuff. Some of this stuff is common to even first year physics courses. I'm a TA at one of the universities, and I find that for instance, simple harmonic motion is really popular, and talked about a lot in the oscillations and waves class. It's actually basic, right? You need simple harmonic motion. You need to go through it, and so I thought I would share some of this stuff. And who knows, I might make it into like a whole series of oscillations and waves. So yeah, this course code was PHY 255. I took the course back in I think it was 20, 2008, right? 2008. Yeah. So it was a long time ago. So yeah, this was 2008 that I took this course. It's still, the stuff that you learn in it is obviously still applicable today. And the textbook is Vibrations and Waves, AP French. Okay? So I thought I'd go ahead with it. So I'm going to start up Zernal, right? Mark executable. Okay, I had to reinstall certain apps. So yeah, sorry, it was a BIOS issue. And so full screen it. Okay, so what I want to do is I want to start by deriving certain equations that we see in simple harmonic motion, and it has to do with small displacements, right? So simple harmonic motion does have to deal with displacements repeating over and over again, right? So periodicity, and the fact that the displacements are somewhat small enough, right? And you'll see, because you have to do some Taylor series expansions and so on. So when you have a displacement x from equilibrium, so you've got this spring, right? Okay, you got this spring, and it is displaced from its equilibrium position by some amount x. Okay, the force exerted on it, if the displacements are small enough, right? The force exerted on it is equal to a Hooke's law, right? So we've seen this before, Hooke's law. Now, this guy, the force, is mass times acceleration. So we can write m times a second time derivative in the x. All right. Now the equation, right, that can solve this differential. The x that can solve this differential equation is a sinusoidal function, right? So I'm going to go ahead and choose sine. So x equals a sine of omega t plus some phase constant, some phase shift. All right. So but if we run this guy, this expression, through the differential equation, what we end up getting, and I want you to try this. Let's do x dot, right? X dot is just a single time derivative, right? dx dt. Okay. So we end up getting omega a cosine of omega t plus phi 0. And so x double dot, right, the second time derivative that you see there, right, is going to be negative omega squared a sine of omega t plus phi, right? So the reason why I picked this is because I know it solves this differential equation, all right? And so what I end up getting is that this constant that I just kind of made up, right, omega, once I throw it through, let's sub in, right? So m x double dot has to equal to negative kx, right? That's my equation. That means that negative m omega squared a, right, times the sine of omega t plus phi 0 has to equal, right, that's what that means, has to equal negative k, no, there's no omega, negative k a sine of omega t plus phi 0. All right. So these are common to both sides, and so is a. So I can just go ahead and cancel, right, both a and the sine. And what that leaves me is with this nice equation that says that omega squared, m omega squared equals k, right? So k, right, is the spring constant. M is the mass of the spring, of the actual object that's actually on the spring, excuse me. So that would be this guy, and k applies to the spring. So basically, this quantity omega equals to k over m, which implies that omega has to be the square root of k over m if we're implying that omega has to be non-negative, right? So we get that nice equation. What's also great is that we note that if this x equals a sine of omega t plus phi is the solution, which we found, right, then I'm going to go ahead and start up a new page, right? If that is the solution, then we've got this nice, periodic sine function that is terrible, but anyways, you get the idea. This should be equal displacement on both sides. So we get that, and we can define a quantity called the period, right? T, where it's like it's periodicity, so the vibrations repeat over time. So every single time you get a full cycle, you get a period T that has a time T that has elapsed, right? So if we take that coordinate, so we had x equals a sine of omega t plus phi 0, right? We've got an argument for sine, and what that means is if we go through, right, a full cycle, okay, then basically it's time t plus some period, right? But that should just equal to the original argument, right, plus 2 pi, because it's gone through a full cycle. Remember, 2 pi is 360 degrees, right? And so what we end up getting, if we expand, right, on the right side, on the left side, okay, what we end up getting is we get cancellations, boom, 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 and we end up getting this nice equation that we usually see in simple harmonics, okay? Simple harmonic motion. Omega t equals 2 pi, and so that implies that period equals 2 pi over omega, right? Now, we found in the previous result was that omega equals, it was root of k over m. So what that implies is that the period is equal to 2 pi, and this guy means that I have to reciprocate this expression, right? It's going to be m over k. Okay, so that's what I end up getting. All right, so that's the period. So that's how you derive the period. Now, if you want to find, let's say, the amplitude, okay, or the phase constant, what you end up needing, right, you need the x value at 0, okay, so the initial displacement, right, and you also need the initial speed at 0, okay, and that's because you've got That's because you've got a second order differential equation, right? So you had this, right, equals, negative omega squared, what was it? Negative omega squared. Actually, no, that's swallowed. Okay. That's swallowed. Omega squared x. So you need both these conditions. We call it x0. We call this v0, right? The initial speed, because the first time derivative is speed. Now, with that being said, so we got to figure out what these guys are. Okay? So we'll do that. So again, x of 0 equals x0, v of 0, or x dot of 0 equals v0. So we need to figure out what those guys are. So, well, x was a sine of omega t plus phi, 0. X dot, right, when you take one time derivative of this, right, so one derivative with respect to time, you end up getting omega a cosine, okay, of omega t plus phi 0. So when you just plug in t equals 0, you end up getting that x0 has to be a sine of phi 0, right? So you just plug in t equals 0, and you end up getting a sine of phi 0. For x dot, right, x dot is just v, so I'm going to call it v0, right, is going to be omega a cosine of phi 0. So now it's the use of these two equations, 1 and 2, and we can find a and phi 0 very easily. For example, you can use, you can divide both sides, right? So you take 2, right? Divide both sides by omega, and you get v0 over omega equals a cosine of phi 0. Okay? And so now what I can do, and I'm going to call this 3, right? Take 1 squared, right, plus 3 squared. So equation 1 squared plus 3 squared. And you end up getting that x naught squared plus v naught squared over omega squared, or v naught over omega, okay, equals a squared sine squared of phi 1, or phi naught, plus a squared cosine squared of phi naught. Okay. Now, there's a common factor on the right side, right? That's a squared. So what I'm going to do is I'm going to pull that out, and I end up getting sine squared of phi naught plus cosine squared of phi naught. But you know from your elementary trig, right, that sine squared of an angle plus cosine squared of an angle is 1. So this ends up equaling 1. And so I end up getting that x naught squared plus v naught over omega all squared equals a squared. That implies that a equals to, and if a is a magnitude, right, it must be positive in this case. So you end up getting the square root of x naught squared plus v naught over omega all squared. And so that's my equation for a. And so I can also determine, right, the equation for phi. That's easy. All I have to do is take 1 or 3, whichever one you want, 2 or 3 out of the choices, and just do this. So I'm going to take 1 divided by 2, okay? So 1 divided by 2, so it's going to be x naught over v naught, right? So literally left sides divide by each other, and then a sine of phi naught over omega a cosine of phi naught. Okay? Now the a's will cancel, very convenient, right? And you know that sine x over cos x equals tan x, right? So this ends up becoming 1 over omega tan of phi naught. Beautiful, beautiful, right? So then omega x naught over v naught equals tan of phi naught. Okay, so that means that if I do tan inverse of both sides, phi naught becomes the tan inverse of omega x naught over v naught, and then getting that result. So there's one, there's phi 0 that you can find, and there is the amplitude that you can find of your oscillation. That is provided that you have omega x naught and v naught. So the initial displacement, the initial speed of the transverse, right, speed, and the angular frequency of oscillation. Okay, so we have that. And so they have this interesting notation, right? So this is kind of like basic stuff that I've run through with you, right? Really basic stuff that I've run through with you. What AP French, which is part of the MIT Introductory Physics series, what they do is they introduce a rotating system. Then they introduce something called a complex number, and the reason why they do this is because the math for studying periodic motion becomes much simpler, especially when you include something called Euler's relation, right? So what I'm going to show you now is some weird math, but the reason why they do this is because Euler's relation and introducing real and imaginary components, that makes things easier for you, for the math side, right? The physics doesn't change, the math side does. And so we usually go with the easier stuff, right? In terms of less tedious work. So we usually choose the less tedious. Okay, so here's what I'm going to do. So we were talking about one-dimensional sort of oscillations. That's all we've been talking about, right? Notice the differential equation has only an x coordinate, right? So this differential equation only has an x coordinate, right? So it's like this. However, what AP French does very well, actually, is that it introduces a second coordinate, and it talks about how that is terrible. Okay. It talks about how circular motion, uniform circular motion, when you have constant speed around a circle, at least in the I got to be careful about what I say here. Now, the motion, right, of this circle, the x coordinate of it and the y coordinate actually, they both oscillate, and the geometric projection of this r vector onto the x-axis, that shadow that it casts is exactly identical to simple harmonic motion that we've been talking about, right? So simple harmonic motion is basically the projection, right, of uniform circular motion. Okay, I'm just going to call it UCM, uniform circular motion onto x-axis. All right. So what this translates to is that there is, if you can kind of represent it in like a two-dimensional system, however, only care about the x coordinate, then as long as that makes it easier for yourself, that's good, right? Perfect. So what they do is they introduce this complex number, x plus j y, right? J is basically the square root of -1. Okay, it's an imaginary number. This is a complex number. All right. So z is the complex number, right? And this guy is the real component, and this guy is the imaginary component, but they're both real numbers. So x and y are both real numbers. Okay. Now, x, right, can be written in polar coordinates. in terms of r and theta. So x can be written as some function of r and theta. Now it turns into just r cosine theta. We know this, right? This is like grade 10 math, okay? R cosine theta. Y equals to r sine theta. All right? So if you plug this in, what we end up getting is z equals r, and then it's cosine theta plus j sine theta. Okay, I want you to plug that in, right? So once we do that, I had a common factor of r, pulled that out. This neat little thing is Euler's relation. It's e to the j theta. Okay, so it's an exponential with an argument of j, which is an imaginary number, times theta. So using this sort of notation, right, is much easier than dealing with like sines and cosines, and the reason why is because of the integrative and differentiative nature of e to the j theta, right? So if you do a differentiation on e to the j theta, it's very simple, right? These exponentials are very useful. So you end up getting just so if I'm differentiating with respect to theta, okay, so d theta, then it just pull out a j and I get e to the j theta. If I do a second derivative, right, so I do a derivative on the original function, right, e to the j theta, then again another j comes out, but now it's j squared then, right? And so that's negative. So notice that if j is square root of negative 1, that means that j squared is negative 1, right? So I get negative e to the j theta. It's very useful, right? So using e to the j theta is extremely useful. Okay. Whoops, my phone went off. Now, how do we get that relation is the question, right? So we need to know how we get that relation. And the idea is that we do Taylor series expansion, right? It seems like in physics, the most useful thing to do is a Taylor series expansion, right? That seems like it's absolutely useful, and it's like the science of Taylor series expansion. That's all it is, right? I remember doing courses over and over and over again, and it seems like no matter what, we had a Taylor series expansion every single class. It was ridiculous. Okay, now Taylor series expansion. Whoa! Okay, Taylor series expansion is f of x, right, equals f of 0. Okay, this is just the definition of the Taylor series, plus x, f prime of 0, okay, plus x squared over 2 factorial, right, times the double derivative at 0, okay, and it keeps on ticking, keeps going, all right? Now, if I work this then, if I do cosine of x, or cosine of theta, let's just say, right? Let's figure out what this is then. So, so the original function at 0, so cosine 0, I just plug it in, right? So cosine 0 plus theta instead of x. I'm not using x, I'm using theta, right? And then this is this is a derivative of cosine of theta, and then plug in 0, so that's negative sine of 0, right? Okay, plus theta squared over 2 factorial. Double derivative would be negative cosine, what am I doing? Negative, and I'm coming back to theta, so negative cosine of 0. Okay, so that's a double derivative. So the double derivative of cosine of theta is negative cos, right? And so if I plug in 0, I get this. Now, what's neat is that cosine of 0 is 1. This guy, sine of 0, is 0, so that's gone. That term is completely gone. And I end up getting minus theta squared over 2 factorial times negative, theta squared over 2 factorial times negative 1, because again, cosine 0 is 1. So I end up getting this. And then the if you keep going, right, you won't get a third factor because that'll have a sine 0, but you get a fourth factor, which will have a factor of theta to the 4 over 4 factorial, right? So that's the expansion of cosine theta. If you do the same thing with sine, right, and I want you guys to try this, okay, you end up getting theta minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial, and it keeps going. Now, what happens, okay, what happens is if you add these two guys together in this specific combination, okay, you end up getting that 1, okay, plus j theta minus theta squared over 2 factorial minus j theta cubed over 3 factorial plus theta to the 4 over 4 factorial. When you just add them straight up, this specific expansion is actually the expansion for an exponential that has an argument j theta. And so we end up getting this beautiful relation that we used previously that I didn't prove as of yet. So that's what we end up getting. And so we've got our way of describing sinusoidal motion. So from now on, instead of using x equals a some periodic function, right, we're literally just going to use z equals some amplitude, right, and then e to the j of omega t plus some phase constant alpha. That's essentially our notation. That's what we're going to be using for periodic motion. And so now we do double derivatives with respect to time on z instead of, or z if you're American, instead of just your x coordinate. So you end up getting negative omega squared times z. Now, so we've introduced two coordinates in x and y, but the thing is, we only care about the real component. So in the end, whatever result you get, you just take the real component of whatever you have, and that's all that matters, right? Because it's one-dimensional, simple harmonic motion. And so that's what we get. That's an intro into periodic motions. In the beginning half, I introduced simple harmonic motion. If you got scared with all the notations and Euler relations and stuff like that, just ignore it if you're not using it for your course. I know that I did for Oscillations and Waves. I loved this course, guys, so much. So thank you for watching. If you can, please subscribe, comment, share. And we just love your support. We love the fact that you're here with us, and it's just such an enjoyable ride for me because I loved this kind of stuff. And what I want to do is actually I want to go into like other things too. So I want to talk about like intro to quantum mechanics. I had a course in quantum 2, quantum 3, right? I want to do more high school courses as well, but also I want to talk about like my calculus courses. Linear algebra, partial differential equations, which is something I started last night, but I haven't posted a video yet. But yeah, thank you so much, and have a good one. And yeah.